Hi, my name's Nick McKeown. My friends and colleagues and I are going to be giving a talk today about the network as a programmable platform. We believe that it makes a very fertile new ground for networking research. Let me start with a story we all know well. The way that we build networks today has changed a huge amount over the last 10 years, much more than it did in the 10 or 20 years before that. I want to focus on three big changes. The first is a change of who is in control, particularly of the control plane software. Before, networks were built from closed and proprietary routers based on as much as 100 million lines of source code running hundreds of protocols. The internet paid a hefty price for this complexity. Routers were bloated and power hungry, and there was little incentive to improve them. In the research community, we talk of internet ossification. The result was that networks were hard to manage, unreliable, hard to secure, and hard to scale. And so large network owners and operators, particularly big data center companies, they started to build their own networking equipment for themselves using white box switches. These would be based on homegrown software, and they would buy merchant switching silicon, and then they would control it with a Linux-based switch operating system. The key here was that this could be done locally or remotely, and then they could develop the code for themselves, or it could be open source that they downloaded from the internet. It saved them money, that's for sure, but it was control that they were after. By owning the control plane, it became easier to fix. They could also add new features that they had wanted for a while, such as traffic engineering, so that they could put more traffic into the network, faster recovery mechanisms so that they could keep the network running more of the time, and intrusion detection schemes and faster homegrown gateways, such that they could prevent intrusions from happening. The key thing was they could add new ideas, which led to faster innovation. So while disaggregation, OpenFlow, and SDN, they were part of how data center companies did it, it was their deep pockets and armies of software engineers that really changed who was in control. The second change is that more recently, network owners have started to take control of how packets are processed too. Switch ASICs used to be based on fixed function pipelines, but with the introduction of programmable switches, developers can now define the forwarding behavior they want using a language such as P4. Programmable forwarding allows network owners and operators to throw out complex protocols they don't need, and then add in proprietary features like telemetry, tagging, tunnels, and more complex functions such as load balancing and caches. Basically, they're after more control. If we're not in charge of how the packets are processed, then we're not really in charge of how the network works. The third big change in how we build networks is that open source has re-emerged as a legitimate and trustworthy way to control networks. In the early days of the internet, new ideas and RFCs were defined by rough consensus and running code. But then equipment vendors stepped in, and essentially everything was closed down. It was as if open source could no longer be trusted. Yet over in the server world, open source Linux, Mozilla, and Apache were proving that the biggest services out on the internet could be based on open source code. So gradually, open source has re-emerged as a legitimate option for networking infrastructure. Today, in fact, almost every large cloud service provider runs a switch or a network operating system based on Linux, such as OVS, Sonic, FBOSS, or ONOS. Network code that was opaque and closed has now become transparent and open. Time and again, successful open source projects have led to faster development, better quality assurance, and more secure code. And as a research community, we can step in and help debug it, add to it, and what's more, we can experiment with completely refactoring it, adding new ways to observe what's going on and new methods of control. So everything I've said so far is probably not new. You will have heard this story before. It's the story of how control has moved from equipment vendors to network owners over the past 10 years. Our talk today takes everything I have said so far as a starting point and asks, so what happens next? Our goal is to tell you our opinion over the next 15 minutes or so. And a spoiler alert, we think there's a huge opportunity for us, the networking research community, to shape how networks will be built in the future. A big and an immediate consequence of what I've said so far is that for the first time, the entire end-to-end pipeline is programmable. The NIC, the vSwitch, and of course the switches. And then if we go into the end host, the kernel ePBF networking code where we can extend the kernel using XDP, and DPDK user space code as well. And most, or perhaps all of it, will be open source. If we'd like, we can change any and all of it however we want. We can program the network horizontally, as I show here in the forwarding plane, and we can program it vertically in the control plane. We believe that we're going to be specifying the behavior at the top, then partitioning and compiling it all the way down to the bottom. No longer will any fixed piece of the hierarchy, whether it's horizontally or vertically, dictate how the whole system works. We can think of it as a programmable platform, a distributed system that we can program to do pretty much whatever we want. And it'll be up to the network owners to decide how their network works. So to recap where we are so far. Networks for the first time will be programmable end-to-end, specified top to bottom, and defined entirely by software. In the rest of the talk, Jen and Nate are going to explain why we believe this creates some unprecedented new possibilities. And then, because of open source, we, the research community, get to take part. But before we get into that, Larry wants to tell us about something big that we should be paying attention to as well.
Thanks, Nick. Control that is both top-down and end-to-end is a worthy goal. But if this picture represents our mental model of the end-to-end path, then we are ignoring the most important network, the 5G mobile network. Now, to the internet-centric eye, the cell network is just one of many possible access network technologies. It's easy to abstract away and ignore. And until now, that's been a reasonable thing to do. 3G and 4G were primarily about connectivity, and bandwidth is bandwidth. There's been little reason to understand the internals of the cell network. What networking researchers do know is that the radio is where the innovation happens, and the research problems there are information theory, not networking. But that's not the worst of it. The cell network has been built using closed proprietary hardware. The barrier to entry for networking researchers has been insurmountable, until now. 5G is different. One, the implementation is opening up and being reimagined as a cloud service, and that puts us on familiar ground. Two, 5G is simply too important to ignore. Backbone networks that connect hundreds of data centers and data center networks that connect tens of millions of servers are important, but will be dwarfed by the 5G network that provides connectivity and new edge services for tens of billions of devices. In short, 5G will be the interface to the cyber-physical world, and we ignore it at our own peril. Now, the details are going to be different, but the opportunity is the same. Let's dig a little deeper to understand that opportunity. Starting with this simplified depiction of the two key components of the 4G network, the eNode B, the base station, and the EPC. Now, the first tip is, this is not familiar to you, that anytime you see a component with an E in its name, beware. The E officially stands for evolved, but that's telephony speak for encumbered by legacy hardware. Now, when you break through all the noise, these two components are essentially an IP router and an L2 switch. And if you think about them in that way, you've made a good start. If we look at the base station in a little bit more detail, we're going to find a protocol stack, and it has a lot of familiar elements in it. At the bottom will be D to A conversion and the radio-specific layers. The middle of the stack has a set of familiar packet processing layers, segmentation, reassembly, ARQ, header compression, and so on. The top of the stack is where packet forwarding happens, because these eNode Bs are forwarding packets to each other throughout the RAN to find the eNode B that can best serve any given user device. Now that's 4G. 5G is going to be fundamentally different, and the starting point is to disaggregate the eNode B and the EPC. There's going to be a radio unit with the radio pieces, there's going to be a distributed unit, and there's going to be a central unit with the forwarding pieces. And the core will be reimagined as a service mesh. Now, 5G aspires to bring best practices in cloud computing to both the RAN and the mobile core, but there are no guarantees. There are strong market forces at play that will continue to try to bundle these. But because open source is part of the equation, there is an opportunity for us to have impact. Now, end-to-end programmability is available in 5G, and it is real, but it is only half the story. As Nick described, we also want vertical top-down programming, and that's happening in 5G too. So the idea is that we're going to take the control elements of this out of the central unit, and that's going to become an SDN controller, and it's going to host a set of control applications. They will be different: handover control, link aggregation, load balancing, and so on, essentially taking those functions that had been distributed throughout all the radio units, pulling them back into a central place where they can be globally optimized. In addition, some of the elements which actually forward packets, can be re-implemented using P4 on programmable switching chips. It's exactly the same as any other switch. They bring packets in, they look things up in the headers, and they forward packets out and output ports. The next piece is that there's a management plane, and that's important because that's where policy is going to be implemented. That leaves us with the multiple control planes that we will have programmable control over. The outer control planes, that's policy, that's a non-real-time control loop. The SDN controller is a near real-time controller, 10 millisecond control loop. And inside of the distributed unit, we will find a packet scheduler with a very tight real-time control loop. That's the scheduler that's deciding which chunks of which packets are going out on the radio spectrum at any given time. Now you may be asking at this point, what about the spectrum? How do I participate in a world that is dominated by large global carriers? And the answer is there is an opportunity through a combination of CBRS in the United States, lightly licensed band that researchers can have access to, running small cells deployed throughout your campus. We actually have a prototype of this called Ether that you'll hear a little bit about later on, but the opportunity is definitely there.
Okay, Larry, we get it. We need to be paying more attention to 5G, and probably we all need to be going to those sessions about wireless at SIGCOMM. So let's get back to the possibilities that this creates for us. Networks for the first time will be programmable end-to-end, specified top to bottom, and defined entirely in software. Because of open source, we, the research community, get to take part in that journey. And because 5G is being redefined in software too, this is going to become a very important part of that journey. I'm going to hand over now to Jen and then Nate to tell us a little bit more about the possibilities that are going to be opening up for us.
But what will network owners do with their newfound freedom to program the network from top to bottom and end to end? We believe they'll want to control their networks better, first by adding new dials, new ways of learning information about their network, tailored to what they're doing to manage their network, to know something about the traffic, its performance, whether that traffic might be part of a new kind of cyber attack, whether equipment has failed, what the current signal strength is for each of the mobile hosts, and so on. To take a concrete example, consider microbursts. Microbursts are the rapid onset of congestion due to bursty traffic. They can be caused by an incast workload in a data center or a cyber attack, for example. And they can lead to rapid increases in packet delay and packet loss, even when the link utilization, as seen by, let's say, statistics available from SNMP, suggest that the link utilization on average isn't all that bad. This is what makes microbursts confusing and very difficult to detect and diagnose. But with fine-grained telemetry in the data plane, it becomes possible to detect and diagnose the microbursts. So a programmable data plane can recognize that a queue is backlogged, say more than half full, and it can also determine each flow's contribution to the queue. For example, an arriving packet, say the green packet here, might be part of a flow that's contributing more than half of the backlog in this queue, whereas another flow, like the red flow, may be a relatively small contribution of the total. More generally, we can design and deploy compact data structures that can answer really important broad range of high-level questions about network conditions, even in programmable data planes that have to operate at very high speed. More generally, we can also use technologies like in-band network telemetry to take information learned at one hop in a packet journey and carry it on the packet from hop to hop to be able to collect detailed information about the entire journey experienced by a particular packet. With this information about network telemetry, we also believe network owners will want to add new knobs, ways to adapt the way their network behaves, to decide whether and when to drop or mark or rate limit or reroute traffic based on information from these dials, or when to hand off a mobile user from one cell tower to the other, and more. All to achieve some high-level important goal. Take, for example, a cyber-physical application running in the 5G network. It might operate under extremely strict requirements for packet delay and packet loss, making microbursts a particular problem. You could imagine in that setting that the network owner might deploy a knob that allows it to mark or drop packets based on the contribution their flow is making to the current backlog in the queue. So when a queue is more than half loaded, a packet like the green packet might come in and be recognized as contributing a significant fraction of the backlog and dropped or marked to be able to cause it to stop contributing so aggressively to congestion that's affecting other traffic, compromising, let's say, a service level objective that the network owner has. In contrast, the red packet, since it's not to blame for the current backlog, might be allowed to be handled normally. More generally, we imagine these knobs and these dials might exist in the data plane or in the control software running on the switch or network interface card or in the centralized controller, depending on the application. Some might require fine-grained operations directly in the data plane. Some might benefit from network-wide visibility that only a controller might have, and so on. More generally, we envision the network now as a programmable set of control loops, where network owners can decide what dials and knobs to connect together with analysis, anomaly detection, optimization, and so on to be able to run their network better, automatically adapting to changes in network conditions. Microburst mitigation is one example, but it's by far not the only one. Traffic engineering, adapting which path the traffic takes in the network based on current measurements of performance. Blocking or rate limiting distributed denial of service attacks. Deciding to do a handoff from one mobile node from a particular cell tower to another to be able to deal with congested spectrum or congestion in the wired network, and more. Stepping back, we think there's a really exciting grand challenge here to make it easy for network owners to state their high-level goals and have a compiler turn that into a control loop with the appropriate dials and knobs to be able to adapt the network automatically without human intervention. And that compiler would produce as its output the distributed software that runs across the network in the controller, in the software that runs on the host and switch CPU, and yes, in the data plane as well, where possible and where needed. We think this is an exciting opportunity to realize high-level goals directly in the network using the programmability that we now finally have from top to bottom and end to end.
Closed-loop control sounds pretty cool. We can get people out of the way and start to build networks with richer behaviors than what we have today. But, and I hate to throw cold water on the idea, it also sounds a bit scary. How will we know that these networks are implementing the behaviors we want? In other domains, we've figured out how to build incredibly sophisticated autonomous systems that we literally trust with our lives. A modern fly-by-wire airplane is responsible for performing basically all of the tasks that a pilot used to, so its hardware and software is extensively validated, both at design time and continuously while flying. While there are still occasional flaws, the underlying engineering principles are sound, and airplanes are the safest form of travel today. So what would it take to build a network that's as trustworthy as an airplane? Well, Nick told you a story about how network owners have been taking control over the past few decades. And it turns out that in parallel, they've also been developing technology for understanding what their networks are doing. In '96, a group of researchers at CMU and AT&T started to explore how you could statically analyze IP forwarding configurations to check network-wide reachability properties. About a decade later, just after SDN emerged, another generation of researchers realized that having decoupled the control plane and the data plane gave you a great interface for doing more systematic forms of verification. And we started to see a flurry of papers and startups focused on network verification tools. More recently, researchers have been building even better tools, including ones that can check the control plane and others for reasoning about probabilistic properties like congestion and latency. And the tools have gotten faster and faster. Note that open source has been a key catalyst. It's been critical to have open interfaces between components as well as the ability to analyze source code. But despite all this progress, today's network verification tools still have some fundamental limitations. One issue is that they work against mathematical models of the network rather than ground truth. And another is that they're mostly advisory in nature. These tools will tell you when something goes wrong and perhaps block an incorrect configuration from being propagated, but there's a real divide between the operational world and the logical world. And there's been very little work on how one could incorporate the results of verification to inform the behavior of the network. So here's one way we could start to put networks under verifiable closed-loop control. First, let's instrument the network to collect fine-grained network telemetry. This is already happening in the open source community through efforts like INT, or in-band network telemetry. But we'll want to go further and be able to collect any data relevant to how a packet is processed end-to-end. Next, once we have these traces, let's feed them into a runtime verifier that can check whether the behavior we're seeing in the network is compatible with what we expect. For example, if the control plane has installed the wrong rule, or a packet was dropped due to congestion, or a flaky NIC caused a packet to be emitted on the wrong link, we can detect it. And last, and here's where all the action is, when we find a violation of a property, we can feed that information into the control loop so that it can actuate the network back into a good state. So there are a few things I find exciting about this approach. First, it's based on very low-level observations of behavior, the telemetry, rather than mathematical models. So this means we can potentially detect faults up and down the stack. Second, it's completely automated. You don't need a PhD or knowledge of a theorem prover to use it. And third, it frees network owners from being conservative in what kinds of control algorithms they use. Just like an airplane has automated flight safety systems to keep the pilot from doing things like putting the plane into a stall, this kind of verification technology can help keep the network in a good state under a wide range of operating conditions. Now, of course, I don't have all the answers. There are a bunch of challenging research questions to answer in the coming years. One issue is efficiency. Collecting and analyzing telemetry for every packet is attractive, but challenging to implement. So can we somehow make it more feasible, perhaps by in-network aggregation or by offloading some of the checking onto the devices themselves? Another issue is expressiveness. Telemetry can keep track of single packet properties, but what if we want to reason about network-wide performance or causality? There's a rich literature on tracing in the distributed systems community that we can mine here. And the third is trust. For runtime verification based on telemetry to be effective, we need to be able to know that the telemetry data itself is good. So just like an airplane combines static analysis of critical components with continuous dynamic analysis of sensor data, we may need to verify some of the functionality running on the devices in order to trust the data.
And so in summary, we believe that networks for the first time will be programmable end-to-end, specified top to bottom, and defined entirely by software. And because of open source, we, the research community, get to take part too. And as part of this, 5G is being redefined by software too, allowing us to shape its future as well. Some new opportunities are created. First of all, to verify that networks are correct by construction, to then measure and validate in real time against the network specification, and to correct bugs through closed-loop control. As a team, we have decided to devote the next 3 years of our work to this journey. We've started our own joint program to build a network on our campuses called Pronto, including disaggregated 5G base stations. We plan to place the entire network under cloud-managed, verifiable closed-loop control, and everything will be open source. If you're interested in taking part in this journey too, here are some places that you could start. First of all, read a couple of microbooks about SDN and 5G. You could deploy real systems on your campus like these that are being deployed elsewhere. You could join and use and contribute to the ONF Ether open source projects. And in fact, you could extend Ether to add new application services of your own, including your own P4 applications. But don't stop at this project. There are many, many other great open source projects to get behind as well. But whatever you do, don't get left behind at the station when the train leaves.
Wait!